Everybody, it's Beej with Lambda School. Today we're going to be talking about subroutines and how the CPU runs them and what they are. So the objective here is to figure out how the CPU does subroutines. We're going to talk about what subroutines are, we're going to talk about how they're used, and also how higher level languages use them to implement functions. So what are they? The best thing to do is to think of them as functions as you already know it from higher level languages. That concept of calling a thing and returning from it exists at a low level in the machine at assembly language as well. So the name of the instruction we use to call a subroutine is call. Of course, this varies based on architecture, but commonly it's call. After the subroutine, which lives at a particular address, runs, eventually a return instruction will be encountered. And with that return instruction, we return to where we were just after the call, just like a function does. After you call math.square-root in whatever your favorite library is, you expect the next instruction after that to execute. So we need to get a way to get back. There are some limitations, though, with assembly level subroutines compared to functions. We've found out so far that CPUs are actually pretty simple machines. Each instruction doesn't really do that much on its own, and it's only larger collections of instructions that get big work done. So what can't we do? One thing we can't do is pass arguments as you're used to doing. The call instruction only takes one operand, and that operand is where to go. It doesn't take any more additional operands to be used as arguments. Likewise, you're probably used to being able to return values from functions, but in assembly language, return doesn't take any operands at all. It simply returns to the caller. But all is not lost. Of course, you can implement these ideas with arguments and return values because other languages do it. So clearly it is possible. Now, in order to make call and return work, we do make use of the stack. So how do we use this thing? Well, when we make the call, we need to remember somehow where we're supposed to come back to after we return later. So we have to store that return address somewhere. Otherwise, return doesn't know where to go. So most CPUs use their system stack to store the return values. And so when we issue a call instruction, we will push the address of the next instruction after the call. We'll push that onto the stack, and that way we have it saved for later. And when we encounter our return instruction, then the return instruction can pop that value off the top of the stack, store it directly in the PC, and the CPU will continue running where it left off before the call. Let's have an example of this. So in this example, we have a short program that loads R0 with 15 and then calls a subroutine, which is down at the bottom of the code. It's got a little space there between the main program and the subroutine, although they are in memory, one right after the other. The subroutine itself adds 10 to whatever is in R0 and then returns. So subroutine, this is the add 10 function. Kind of contrived, admittedly, but hopefully good enough for demonstration purposes. So the first thing we do is we load R0 with 15, and then we're going to call add 10. So after we call that, R0 should probably be 25. We've also got on the right side of this slide, we see the stack, which is currently empty, but we'll make use of the stack to know where to come back to. So first of all, we load R0 with the value 15. And then I'm going to load R1, register 1, with 0B. Why 0B? Well, if we look down at the bottom of the code there, where the subroutine starts, 0B is the address of the beginning of the subroutine. This is where we want to go. And so I load R1 with the address of the subroutine, where we want to go. And then the very next line is call R1. And this is going to move the program counter down to that address 0B. But first, we need to keep track of where we're coming back to when we get our return. And what instruction do we want to come back to after we return? Well, after we return, we want to execute the next thing after the call, which is that PRN instruction at address 8. So we want to return to address 8 after this call. So what we do is we take address 8 the one very next after the call, and we push that on the stack. So now the stack has 8 on it, which is our return address that we want to come back to after the subroutine executes. So the call instruction first pushes that on the stack, and then it changes at the PC to be a 0B at our subroutine. So now we have called the subroutine. The subroutine adds 10 to register 0. Remember, from address 0 way up there at the top, register 0 is 15, so after this it should be 25. And then we get our return instruction. The first thing return does is it pops the stack. So we got 8 on the stack. It pops that value and it puts it directly in the program counter. So the program counter is going to become 8 after this. So we pop the value off the stack, store it right in the program counter. Now the program counter is 8. And we're going to continue running. Right after we left off, we'll print R0, which should print 25 at this point, and then we halt. So you can see that we've called out to a subroutine, we've returned back from the subroutine and continued instructions where we left off, and we use the stack to store that return address. So what are some of the uses of subroutines? Well, you're going to use them in any place that you use functions in a higher level language, and for any of the same reasons commonly surrounding the idea of not repeating yourself. Don't repeat yourself. But any place that you might think of using a function in a higher level language, you use a subroutine in assembly language. And indeed, those higher level languages eventually they use call and return deep down. So they have to implement functions somehow, and those functions have to become machine code instructions at some point. So typically they use call and return to make that happen. So last slide. These are some challenges for you guys. You can go ahead and hit pause, run through these questions, and see if you can test your knowledge of how subroutines work and see how you might implement some higher level ideas in subroutines. As always, thanks for watching.